Hello everyone, and welcome back to another lecture video. In this lecture video, we're going to be concluding our review of linear algebra with Linear Algebra Review Part 2. So, of course, the name isn't very creative, but it's the end of the linear algebra review, so I take it that most of us will be pretty happy. It's no secret, linear algebra to me, it's not the most fun topic. It's something I can't really visualize, which makes it hard for me to, I don't know, grasp the concepts, I guess. But again, in this particular course, we are going to look at real-life applications. So hopefully, after this, once we start getting into the applications such as solid mechanics, it'll begin to make much more sense why we are learning linear algebra. So again, I kind of mentioned this in the last video, but part 2 here, we're going to start talking about linear maps. All right. So when we get into linear maps, what is a linear map? Well, by definition, a linear map, which I'll call T, between two vector spaces v and w, is a function such that for any vectors u and v and any scalars alpha and beta, t of alpha u plus beta v is equal to alpha tu plus beta tv. Now when we look at this, of course, it doesn't really make any sense, but we can use this definition to easily see what a linear map is. For example, if I had a function from R to R, a linear map could be alpha x. Nice and simple. We have a scalar alpha, we have a vector, in this case it's just a 1D vector x. That's a linear map. Now when we look at this, what makes it a linear map? Well, let's say that we had the linear map 7x. So again, 7x is just a case of alpha x. We can see that with this, we can actually do something very special. Now when you guys learn linear maps in linear algebra, it's a little bit more complex. They use a lot of definitions that don't make a lot of sense to me, but this is how I want you guys to think of linear maps. What we do is we have an input, which in this case is 2. We put it through our linear map, which in this case is 7x, so we go 7 multiplied by 2, and we're given an output, which is 14. So this is how I think of linear maps, and I personally think this is the best way to think about it in this course. We have an input, we put it through our linear map, and we receive an output. Now, it's not just limited to one-dimensional maps. Of course, we can have two-dimensional maps. So we can have a linear map from R2 to R2, and that would look something like this, where we have a matrix here, alpha 1, 1, alpha 1, 2, alpha 2, 1, and alpha 2, 2, and we multiply it by the vector x1 and x2. So let's say that our linear map in this case, our matrix there is 7, 1, 4, and negative 2. I can do the exact same procedure I did on the left, where I can input a vector x. In this case, it is 1, 2. I put it through my linear map over here, and I receive an output. In this case is 9, 0. Now this is great for finite element analysis, because if you think about the finite element program as a whole, or the majority of computer programs as a whole, we usually put some input into the computer does its map, and we receive an output. And that's exactly what we're going to be doing in the finite element method, as we'll discuss a little bit later. Now, one thing that you guys are going to learn, or learn the hard way, is that in this particular course, and I'm going to emphasize that, in this particular course, linear maps between finite dimensional vector spaces can also be referred to as tensors. So for example, above there I said the matrix alpha 1, 1, alpha 1, 2, alpha 2, 1, and alpha 2, 2, but I can also refer to that as a tensor. So I may not always say matrix, I may call it a tensor instead, but for the purposes of this particular course, and I want to emphasize this, because there is a difference between a matrix and a tensor, but for this particular course in Euclidean vector space, I can use them interchangeably. So if you hear me say matrix or you hear me say tensor, they're going to be interchangeable, so you don't have to worry too much. All right. So when we talk about linear maps, there's actually a bunch of different types. A map or a function between sets can be A, injective, which each input has unique output. And that may sound a little bit crazy right now, but don't worry, we're going to show you guys a picture to show you exactly what that means. The second type is surjective, so every output has an input. Bijective or invertible, where in this case, the function or the map is both injective and surjective. And finally 4, which is none of the above. Now the reason why I'm showing you guys this is because map type number 3 here, bijective, which means that it is both injective and surjective, that's going to be very critical moving forward. As you guys are going to see, most of the linear maps that we deal with in this course, they're going to be invertible, therefore they are bijective. What exactly does injective and surjective mean? Well, let's look at an example. Remember how I said we had a nice linear map where f of x is simply just alpha, which is a scalar, multiplied by x. Now, if we were to look at this function more closely, we can see that there is only a single value of x associated with each value of y. Therefore, one input is associated with only one output and vice versa. Therefore, in this case, we would say that this function is injective. Now, it still may not be clear what injective is, but once we get to the second example, it'll be very clear what injective is. Now, if we were to look at surjective, we can see that every output on that y-axis is accounted for. Therefore, if I wanted the output, let's say -5, well, there is a value of x to give me that output. If I wanted the output, let's say 10, well, there is an input of x that will give me 10. And since every output is accounted for, we say that this function is surjective. Now, remember that we said if something is both injective as well as surjective, we actually say that this function is bijective or invertible because again it is both injective and surjective. Now you guys may look at this example and say, Clayton, well, it's still not very clear what injective or surjective is. Well, let's look at a second example, and in this case it'll become quite clear. So now let's look at the function where f of x is equal to the absolute value of x. This is where things start to change. If we were to draw a horizontal line there, we see that for the output of, let's say, +2, there is actually two inputs that return that same output. Again, if I wanted the output +2, I can input either x is equal to -2 or x is equal to +2. So therefore, since there are two inputs that lead me to the exact same output, we would say that this function is not injective. Now, if we were to look at this function and say, is it surjective, we can see that there is a whole range of outputs, in this case the negative region, that actually do not have an input. Let's say that I wanted the output -5. There is nothing I can input into this linear map that returns me with that output. So in this particular case, we also say that the function is not surjective. So hopefully by now it becomes a little bit more clear what type of linear maps we are dealing with. All right. So moving forward, we're going to talk about determinants. Now, determinants are something that we talk about in linear algebra very commonly. I guarantee that almost all of you guys will know how to calculate a determinant. But why do we use determinants? As you guys are going to see in this course, it's going to be very important to know what a determinant is and how to calculate it. Now, the determinant of a matrix is a real valued function, meaning that if you guys take a determinant of a linear map or a matrix or a tensor, you guys are going to get just a single value. Now, this is very important because it indicates two things. First of all, the invertibility of the matrix or the tensor, and the second one is the change in area after a linear transformation. Now, you guys may be very familiar with the first part. Determinant indicates invertibility, but the second part there, that change in area, as you guys are going to see when we get into isoparametric elements, that's actually going to be very important, and we're going to rely on that a lot. So we basically have two scenarios in this course. In linear algebra, we have infinite scenarios because we deal with infinite vector spaces. But in real life, we are limited to usually 2 by 2 or 3 by 3. So the second dimension or the third dimension. So if we look at scenario 1, 2 by 2 matrix or tensor, so I have my matrix M, which is components A1, A2, as well as B1, B2. Well, the determinant of M is actually very easy to calculate, and it's represented by putting those absolute value signs around our matrix or our tensor, and it's equal to alpha1 times B2, or not alpha, A1 times B2 minus A2 times B1. So for 2 by 2, very nice and simple. If we go into 3 by 3, which would be more like the third dimension, we can have a matrix A1, A2, A3, B1, B2, B3, and C1, C2, C3. And the determinant of that is actually just going to be A1 multiplied by B2, C3 minus B3, C2, etc., etc. So we have nice formulas for these determinants. It's not too hard to calculate, which is good because since we're going to be using them so often, we want the calculations to be nice and easy. Now, if we were to look at the formula for the determinant of a 3 by 3, as you guys may remember from the first linear algebra review, the determinant of this matrix is actually the triple product. So if I were to have my matrix consisting of 3 vectors, A, B, and C, well, the determinant of M is actually going to be A dotted with B cross C. All right. So if we were to look at the definition above, I said the value of these determinants is, first of all, indicating the invertibility of a matrix. Well, how exactly does it do it? Well, if we look at a determinant and we calculate it, we basically have two scenarios. The first one is if our determinant of our matrix is equal to 0, so equal to 0,
our matrix is actually not invertible. Therefore, the rows of that matrix are linearly dependent. So as you guys remember from the last little lecture video, we know what linear dependency means. Now, the second scenario is if the determinant of the matrix does not equal 0. Therefore, our matrix is invertible and our rows are linearly independent. And as we discussed when we talked about types of maps, we are going to be mainly dealing with invertible matrices. Therefore, the determinant of our matrix should not equal 0. If you guys are doing the finite element method, you get the determinants equal to 0. Well, something may or may not be a little bit wrong. All right, so moving on, we have eigenvalues and eigenvectors. Now, these were something that I learned in linear algebra, and I say, wow, these are kind of interesting, but completely useless. And boy, was I wrong. Eigenvalues and eigenvectors are going to pop up everywhere in this course. They're going to signify something very, very special when we start talking about both strain matrices or strain tensors as well as stress tensors. All right, so the eigenvector of a matrix M is a vector that when transformed by matrix M retains the same direction. And the magnitude of expansion or contraction of the vector after transformation is called the eigenvalue. Now, as you guys may know, when I look at words, I don't like words. It's hard to picture exactly what I'm saying, so let's look at an example. Let's say that I have the basis set E1 and E2, and inside that basis set I have two vectors, U and V. Now I take those vectors and I'm going to apply that nice linear transformation, my linear map M, from R2 to R2. And what happens is two different scenarios. So right there, you guys can see I have my vectors U and V. They're kind of shaded out, and that's the original position of these vectors. So the first scenario I can have is when I transform, let's say, vector U by transformation matrix M, I can see that both my vector changes direction as well as changes in magnitude. All right, so this is the most typical scenario, but there's a very special scenario. So let's say that I take my vector V and transform it by M. As I can see, it does change magnitude, so it either expands or contracts, but it maintains the same direction. So this is going to be the most important thing, because if we look at MV, well, it's actually equal to just some scalar lambda multiplied by v, because it maintains that same direction. It just expands or contracts by a magnitude of lambda. So if this is the case here, as the direction of v did not change after the matrix transformation M, what we do is we say that v is actually an eigenvector of M associated with an eigenvalue lambda. All right, so hopefully this clears up what exactly an eigenvalue and eigenvector are, but how can we calculate it? Let's start with the eigenvalues. So to determine the eigenvalues, which we said is lambda, of a matrix M, we basically just solve the following equation. The determinant of M minus lambda I is equal to 0. So just like before, in this particular class, we have two scenarios, 2D and 3D. So if we start off with the 2D matrix, or a 2 by 2 matrix of A1, A2, and B1, B2, we can easily find the determinants of M minus lambda I as the determinants of A1 minus lambda, A2, B1, and B2 minus lambda. Since we know all the components in there, we can just apply our nice easy formula, and as we're going to see, we get A1 minus lambda multiplied by B2 minus lambda minus A2 B1, and of course we said that this equation is actually going to be equal to 0. So if we were to look at that equation at the end there, we basically just have a quadratic equation. It's equal to 0, therefore we can solve for our two values of lambda. Now if we look at scenario number 2 here, which is a 3 by 3 matrix, so we have A1, A2, A3, B1, B2, B3, and then C1, C2, C3, we can just apply the same methodology. I go with the determinants of M minus lambda I, so all of those diagonal components of our matrix have that minus lambda tacked in, and therefore we can create a nice equation which we know is equal to 0, and from here we can say we have a cubic equation, therefore we can solve for the values of lambda. Now one of the key takeaways here is in scenario number 1 we have a cubic equation. In scenario number 2 we have, in scenario 1 we have a quadratic equation, and in scenario 2 we have a cubic equation. So therefore each matrix C could have more than one value or more than one eigenvalue. There's different possible values of lambda depending on which scenario you are in. And this is going to be important once we calculate the eigenvectors. So the eigenvectors of a matrix, which I'm going to call P, are associated with a particular eigenvalue lambda. Now, we determine them just by solving the following equation, where MP is equal to lambda P. So if we were to look at this equation, since we have that lambda in there, we are actually going to have to solve this equation as many times as we have eigenvalues. So if I have two different eigenvalues, well then I need to solve this equation twice because there's going to be two different eigenvectors. All right. So if we were to look at scenario number one, where we have m, which is equal to a1, a2, b1, b2, well, we can just substitute everything in. I have my matrix m, a1, a2, b1, b2, multiplied by a vector p, p1, p2, and that's going to be equal to lambda, which is multiplied by p1, p2. Now keep in mind, at this point, we know what m is, and we know what our eigenvalues lambda are. The only unknown in this equation are going to be that p1 and p2. So what we can do is we can expand this out into two different equations, and as we can see, we basically have two equations with two unknowns. Therefore, all we have to do is solve for p1 and p2. Well, at least it looks that easy, but there's actually going to be an infinite amount of solutions for these, because remember, these eigenvectors, they just show a direction. So therefore, if I had the vector 4, 2, it's the exact same direction as the vector 2, 1. That's why we have those infinite solutions. So therefore, in order to solve these two equations, what we actually need to do is assume a value for p1 or p2, and then we can solve the equation for an actual value. All right, so it's actually not too bad. If we look at scenario 2, 3 by 3, same methodology, we have m multiplied by p is equal to lambda p, and in this case we have three equations with three unknowns. Sounds simple again, but of course we have infinite solutions. So in this particular case, we assume a value for p1, p2, or p3, so just one of them. We don't assume values for all of them. We just assume a value for one of them, and then we solve. Now you may say, Clayton, what do you assume for a value? Well, typically I go to the last value. So in scenario 1, I'd look at P2. In scenario 2, I would look at P3, and I just set it equal to 1, and therefore the solution actually becomes very simple. So that's eigenvalues and eigenvectors. Not too bad, but you guys will definitely see these pop up once we start talking about stresses as well as strains. All right, so moving on, we're going to start talking about invariants. And invariants of a matrix M are values that remain constant after a change of basis. So as you guys remember from the previous lecture, if we change the basis set, which is that E1, E2 into, let's say, E1 prime and E2 prime, the components of our matrix C, or the components of our vector, they would change. However, these invariants are values that even after that change of basis, they do not change. Therefore, the invariants of a matrix M, as well as the matrix M prime, which is QM, Q transpose, they're going to be the exact same. And this can be very important once we start talking about stuff like plasticity. So the first invariant, very, very simple to calculate, which we say is I1 of M, is called the trace of M. So that's why I have that TR of M, because it's typically called the trace of M. And this is equal to the summation from I equals 1 to 3 of MII. Now looking at that, you guys say, well, summation, Clayton, that just looks like garbage. Show me exactly what it means. Well, to put it simply, the first invariant is the sum of the diagonal terms. So if I had a matrix M, which is A1, A2, A3, etc., etc., well, the first invariant of this matrix is just going to be the summation of those diagonal rows. So I1 of M is just going to be A1 plus B2 plus B3. Not too bad. The second invariant is something that gets a little bit more complicated, and that is the second invariant is equal to 1/2 of the trace of M squared minus the trace of MM. All right, so if we look at this closely, well, the second invariant is actually just a function of the first invariant of the matrices M and then MM. That's a bit of a tongue twister for me. Now, the key mistake that students make here, and you guys are too smart, you guys are going to say, all right, Ken, who makes that mistake? I'm way too smart for this. But that is this component right here. If we look at that last component, it is the first invariant of MM. It's not a typo, it's not a mistake, that is actually the matrix MM. So if we want to calculate that second invariant, the first thing we're going to have to actually do is calculate what is our matrix MM. Most students think it's a typo, they just think it's I1 of M. Please don't do that. You'll get the wrong answer, and then unfortunately you'll have to get some marks deducted. All right, but again, you guys are too smart. You guys will definitely not make that mistake. Now finally, the third invariant is actually one that we've already talked about, and that is the determinant. So the third invariant, I3 of M, is simply just the determinant of M, and we've already discussed how to calculate that. So overall, invariants, they're not too bad. The first one, very simple. The third one, again, very simple. The only real trick comes into that second variant with the matrix MM. So moving forward, we can talk about something called orthogonal tensors. And these are something very common when we start talking about coordinate transformation tensors, which you guys have already seen before. Those are those tensors Q. So a tensor Q is deemed orthogonal if Q transpose of Q is equal to I, where I there is the identity matrix. And because of this definition, these orthogonal tensors possess some very nice properties. The first one is the determinant of Q is equal to plus or minus 1. Now this is always the case. If you take the determinant of a matrix and it's somehow not equal to plus or minus 1, well, it's definitely not going to be orthogonal. All right? And since this determinant is equal to plus or minus 1 and not equal to 0, we know that this tensor will always be invertible. Remember, a tensor that is not invertible has a determinant equal to 0, which is out of the range of possibilities for these specific tensors. Now, there's going to be two possible scenarios. If we look up there, plus or minus 1, well, why plus or minus 1? Well, if the determinant of Q is equal to plus 1, Q is associated with a rotation. And that's what we saw before. As you guys remember from the last lecture, we were able to rotate that basis counterclockwise. Therefore, the determinant of that matrix that we derived, that's going to actually be plus 1. Now, the second scenario is if the determinant of Q is equal to negative 1, therefore Q is actually associated with a reflection. So this makes for a very good examination question. Is Q a rotation matrix or is it a reflection matrix? And again, matrix, tensor, they're interchangeable. So no matter which one you hear me say, it's going to mean the exact same thing in this course. Now, the second property, the rows of Q are orthogonal. So if I have a matrix Q and the rows are A1, A2, A3, B1, B2, B3, C1, C2, C3, well, therefore those vectors that make up the rows, which is A, B, and C, they're all going to be orthogonal or perpendicular to each other. That means that A dot B is equal to A dot C, which is equal to B dot C, and that's going to be equal to 0. And we discussed why this is in the previous lecture. Now, the third one, kind of the same as the second one, is that the columns of Q are orthogonal. So if I have three vectors A, B, and C, but in this case they make up the rows of Q, well then again A dot B is going to be equal to A dot C, which is going to be equal to B dot C, which of course is going to be 0. And finally, the fourth property is the product of two orthogonal tensors is also orthogonal. So it says orthonormal, but I meant orthogonal there. This is one of those things that, as we're going to see when we start talking about constitutive laws, this is going to lead into some very nice proofs. All right. So moving forward, we got symmetric tensors, and these are going to be something that pop up everywhere. But these are something that's actually a very nice thing. Symmetric tensors are going to be your best friend in this course, as well as any other courses like solid mechanics or continuum mechanics, stuff like that. So a tensor S is deemed symmetric if S of the matrix or the tensor S is equal to the transpose of itself. Now, what exactly does this mean? Well, it means that the off-diagonal components are the exact same. So Sij is equal to Sji. And as I was saying, this is actually a very good thing. In engineering applications, most of what we deal with is going to be symmetric tensors. And this is nice because it simplifies things. So you may say, Clayton, how exactly does it simplify things? Well, let's look at a tensor S. If we look at a tensor S, which is 3 by 3, we see that it has 9 components, S11, S12, S13, etc., etc. However, if it is symmetric, therefore those off-diagonal components are going to be the same. Well, instead of having S12 and S21 as different values, we know they're actually going to be the same. So therefore, we actually go from 9 components all the way down to 6 components, which is great because it just means less calculations for you. And no matter what the scenario is, if you have less calculations, it's usually a very good thing. All right? So of course, these symmetric tensors, they have some unique properties themselves. The first one is for any two vectors u and v and symmetric tensor S, S multiplied by A dot B is actually equal to A dot S of B. All right, so one of those things that again comes in handy when we start talking about proofs, but other than that, you won't really see it too much. The second one, which you guys will see, is the coordinate transformation of S, which is S prime, which is equal to Q times S times Q transpose. That's also going to be symmetric. And we're going to talk about that in the next slide. It's something that's actually very beautiful, and it's going to help us a lot, again, once we start talking about stresses and strains. And finally, if an n by n symmetric tensor has n real not if, a n by n symmetric tensor has n real eigenvalues associated with n orthonormal eigenvectors. So this is going to be one of the things that we're going to talk about in conjunction with point number 2 here. So what we're going to do is we're going to take point number 2 and point number 3 and see what happens if we combine them together. So this is called diagonalization. And what does that mean? Well, if a symmetric tensor S is transformed by a coordinate transformation matrix Q consisting of the eigenvectors P, Q, and R of S, the resulting tensor is called diagonal. Now again, bunch of words, Clayton. I don't know what those mean. Show me what those mean. Well, let's say that we have a symmetric tensor S. So if we look at the components, we see that S12 is actually the same as S21, something like that. So we have a matrix S there, it's symmetric, and we have a coordinate transformation matrix Q, and the rows of the Q are actually the eigenvectors of S. So we see that the first eigenvector, P1, P2, P3, that is the first row of Q. Now, what makes this so special is if we were to do a coordinate transformation of S by this particular transformation matrix Q, so we have S prime is equal to QSQ transpose, we see that the following matrix is diagonal. Now, what makes this so special is that the diagonal components of this matrix are actually going to be the eigenvalues of S. And if we look at the off-diagonal components, they're all equal to 0. Therefore, if I know, let's say, the eigenvalues of S, or eigenvalues of S prime, eigenvalues of S, I know what S prime is, stuff like that, and it's going to be very important moving forward. Now, again, we talked about invariants. Invariants don't change after a coordinate transformation. Therefore, this matrix above, this S prime, those invariants actually still apply. So the invariants of S are actually equal to the invariants of S prime, and in this case, we can actually make the invariants a function of the eigenvalues. So the invariant 1, again, that's the trace or the sum of the diagonal components. It's just going to be lambda p plus lambda q plus lambda r. Very simple to see. The second invariant of S becomes much more simplified, where it's equal to lambda p multiplied by lambda q plus lambda p multiplied by lambda r plus lambda q multiplied by lambda r. And finally, the third one is the determinant. And remember, the determinant of a 3 by 3 was a very long formula, but because since we have many of the components equal to 0, the determinant's actually just going to be those 3 diagonal components multiplied by each other. And these are called the principal invariants. All right, so that's going to wrap up our linear algebra review. If you guys look at this and say, you know what, Clayton, it's just a fancy tongue twister again. It's just a bunch of fancy math. Well, don't worry too much, because starting now, we're going to actually get into solid mechanics. So everything that we've discussed here in our linear algebra review, we're going to apply it to real world things, which I find is very nice. If I were to look at a matrix, well, to me, it's just a bunch of numbers. Who cares? You got a bunch of numbers? Cool, you're a nerd. Nothing too special. But when I start talking about, let's say, the stress components of a cube, and those are represented in a matrix, well, then I'm able to visually see what that matrix or what that tensor is representing. And I don't know. Personally, I just find that helpful. I'm not too sure about you guys. Maybe, maybe not. I guess only time will tell. All right, so that concludes this lecture. Thank you guys so much for watching. I will see you guys in the next lecture video.